The broader initiative in which we're doing all this work is called the core stack, commoning for resilience and equality. So just to give a high-level picture, basically we're trying to bring to develop a good place-based understanding, right, at a very local level of any of these places, so that we can think about what kind of ecological stresses it might be going through or what sort of actions can be taken. We are trying to bring a lot of different data sets together. Some of these we are generating in our own lab, tracking land use, land cover over time, and hoping to use Tessera and other things for it, and similarly water stress and so on. On those, we then compute for different spatial units like villages or watersheds, micro watersheds, we compute a whole bunch of indicators. And that's why we're also trying to do more modeling, like the hydro GPU work that I talked about. And all of these, we're in the process of now, these are all currently running as isolated pipelines, but we're now trying to bring them together in the STACD method that I talked about. So while all of this is accessible openly and through APIs, we're also building a bunch of dashboards. And here the primary user is either NGOs or civil service organizations working in these areas, or community members, farmers, and so on. So I'll show a quick demo of some of these things. So for example, Know Your Landscape is meant more for like a large NGO to plan, right? What sort of works they should do in different parts of an area. Commons Connect is now an Android application, which is meant to be in the hands of somebody in the community, like a community volunteer or an NGO frontline worker, through which they can do micro planning, that what are good places for farm ponds or check dams and so on. And then we're doing a bunch of work around impact assessment and everything. And the outputs from these tools, we try that they can be plugged into different government schemes. These government schemes in India, they finance many of these natural resource management structures, or different sort of incentives for farmers to move to natural farming and such things. So I'll give a quick demo of Know Your Landscape to show what this looks like. So we've automated pipelines to generate all of these data sets at equivalent of a sub-district level in India. And these are all, it takes us about a day to generate a lot of these data sets for any given area. So you can also look at a report. These blue boundaries are micro watershed boundaries, black boundaries are village boundaries. So you can do things like, you can look at a report of a micro watershed where the NGOs can understand what is the terrain like in the area. There's some pre-computed stats like how much area is under what kind of a terrain. And similarly, change analysis that over the last, since 2015, have trees changed to built up, or has area come under from trees to cropping. Then another important parameter is cropping intensity, that in India, a lot of the agriculture is rain-fed, which means that there's, in many areas, there's less irrigation water available. So how many areas are able to plant just one crop in a year, which is during the rainfall season, or whether areas are able to do two crops or three crops and so on. So these sort of changes can be seen. Land use, land cover graphs. How is surface water availability similarly changing? So for example, this is a dam on one side, and we basically do seasonal water detection, right? So the dark blue is perennial water. The light blue is sort of water that stays during the rainfall and the post-rainfall season, and rest of it is just seasonal water. So these kind of things, when put together, they can help us understand which areas might be, right? So we also bring in, for example, drought analysis and so on, right? And how is groundwater behaving in the area. So all of these things put together for a given unit can help in terms of planning, right? That which areas are more drought prone, and also they have some kind of a surface water stress, they have some kind of a groundwater stress. And then we also pull in data of different villages, that what are the villages in this particular area. So there's also, India has a policy in place for affirmative action for lower caste communities. So some of those stats we're able to see. And then there's a lot of government schemes that fund many of these activities. So which villages have had what kind of works is also here, right? So this also, at this unit level, we then also allow people to play around, that they can start defining what we're calling patterns. That let's see areas which are mostly plain, right? So behind this, we have all these raster layers of which areas might be at the bottom of V-shaped valleys or U-shaped valleys. So there's an algorithm called the topological position index algorithm that we use to derive this map. And here we are basically just discretizing it in coarse categories, that which areas are plain or they have a mix of plain and slope. So there's some hilly areas over here. And then bringing in this climate data, that let's see which areas are also more drought prone, right? So now you know that these areas are more water stressed, right? And likewise, which areas also the surface water sort of dries up after the monsoons. Yeah, so these things can help you, right? Likewise for restoration, right? Reduction in tree cover and so on. So these can help NGOs or anyone working in these areas to figure out, right, that for areas following this kind of a pattern, what could be done. So some of the other interesting things, right, that this also allows is that you can start writing expressions of this sort, right? Or right, that in areas where the aquifer is of some type and the terrain is a mix of plain and slopes and so on, right? What might be things that you can do? So you can write logical expressions, but what we are also trying is that because local organizations working in these areas, they really understand what works. So can we use this as a way to codify their local ecological knowledge and traditional knowledge? How much more time do I have? Okay, then I skip this demo of the application. Here, it's now in the hands of somebody from the community. And what this allows people to do is, there's some decision support tools built into it, that is this area good for a farm pond or a check dam and so on. And then people can fill a form that for that particular structure, what are the dimensions and so on that they want to plan. And they can generate a village development report or a village development plan, which can then be submitted to the government officials. So this is really helping, because now you're able to get more data-driven, bottom-up planning happening. And it's also very important for empowerment, because often what happens is that communities do want many of these structures, but they're not able to justify to senior government officials about why they want it, and right, there's a lot of corruption and so on. So here we're kind of giving credence to what the community is saying, plus we're constructing a digital trail which brings transparency. So now it becomes much harder for anyone to sort of deny these things. So let me then quickly show this demo of STACD, which I talked about earlier. So this is like a toy example. Right, that let's say you have some of these layers, you want to run a LULC on it, you want to run a terrain classifier on it, and then you want to sort of know that areas which are mostly plain, what sort of, are they forested or are they cropped, right? So this is this LULC cross terrain kind of a vectorization. Here, we express this in the STACD format, and I hope
the user specifies the entire workflow in terms of
my
YAML
student
config
Saharsh.
files. There is dag.yaml that defines the entire workflow. Then there is algorithm repo that defines the actual instances, their assets, the execution modes such as Docker or API based, and then the other details required for this execution modes. Then there is also the dataset repo containing the initial datasets required and the DAG generator script that takes all these YAML files and creates our DAG that is fed to the Airflow execution engine. Then we go on to execute the Airflow in backend, and we can see our DAG and the Airflow dashboard containing all the dataset nodes and the dependencies that we defined in the DAG. Then we trigger this DAG based on certain trigger parameters, and you can see that this DAG has been triggered for the given year and the given region, and all the nodes are successfully executing. The determine execution path is for the selective recomputations that we have defined in the STACD format. As you can see that Airflow has triggered both of the algorithms in two separate Docker containers, and then the scripts run inside these Docker containers and they trigger tasks on Google Earth Engine that create assets in turn that will be used by the next set of algorithms in the pipeline that has been defined in the YAML. So you can see that parallel pipelines can execute simultaneously the terrain vector and LULC. We can also see the logs of the execution of the script on Docker container for any debugging or error resolution purposes. The triggering of the algo leads to a blocking call, and Airflow will only move forward once the asset IDs of the created asset on Google Earth Engine or any other platform is returned by the algorithm that has been triggered. As you can see, more and more algorithms are triggered. You can also do lineage visualization by providing the dataset name and the version, and the backend database fetches the lineage details for you so that you can visualize the lineage of any particular dataset and its version correctly using our Airflow dashboard. Finally, all the nodes have successfully executed and created their assets on Google Earth Engine by triggering with the help of Airflow. As you can see on Google Earth Engine, all the assets have been successfully created for each of the algo, raster, vectors, everything has been created. We can check these assets also. As you can see, this is the asset for Dumka Masalia LULC map. This is the asset for vectorization, and it shows all the features and properties as well.
So, yeah. Where we are currently, there's all these data sets, and right now it's of course us doing it. But we're trying to move everything to the STACD format so that it's not like individual pipelines, but the whole DAG can be triggered for given locations. So here, a lot of the computation actually happens on Earth Engine, or some of it happens locally on GPU workstations. And all of these datasets are then published onto GeoServer, from where some of the front-end tools that I was showing, Know Your Landscape and so on, they visualize. But potentially, the whole idea behind going forward with this STACD approach was that these DAG specifications can then be shared with other people. So potentially you can have anyone else setting up local instances and writing their own DAGs in YAML and executing them. And then thinking about new use cases, right? Not just the ones that we've done over here, but they can think of, right, maybe restoration or grassland restoration and so on are more important in some areas. So that can move forward, yeah? So I'll stop here.
Writing DAGs in YAML is one of my great regrets from working on Docker Compose, but it's good to see it being used for good purposes here. Does anyone now? Adi's already been on stage and has asked questions. So if no one's got any burning questions, we can discuss the tools and stuff at the evening session. Oh, Dominic, go right ahead.
So what about when they're not a DAG? What about when you have feedback cycles, which often does happen for certain kinds of models?
Yeah, I mean, we've not thought that much about it, but especially when some of this retraining is meant to happen and stop at a particular point. So we do need to think about it. Yeah, for sure.
Let's thank Adi again.